Let's look at the fields of force. Newton's universal gravitational law and Coulomb's law enable us to calculate the magnetic as well as the direction of the gravitational and electric forces, respectively. However, one may question what are the origins of these forces? How are these forces transmitted from one mass to another or from one charge to another? The answers to A is still unknown. The existence of these forces is accepted as it is, and this is why they are called the basic forces of nature. To describe the mechanism by which the electric force is transmitted, Michael Faraday introduced the concept of electric field. According to this theory, it is intrinsic property of nature that an electric field exists in the space around an electric charge, and this electric field is considered to be a force field that exerts a force on other charges placed in that field. For example, a charge q produces an electric field in the space surrounding it. This field exists whether the other charges are present in space or not. However, the presence of field cannot be tested until another q0 charge is brought into the field. Thus, the field of charge q interacts with q0 to produce an electric force. The interaction between q and q0 is accomplished in two steps. A. The charge q produces a field, and B. The field interacts with charge q0 to produce a F on q0. These two steps are illustrated in figure 12.4. And in this figure, the density of the dots is proportional to the strength of the field at various points, and we may define the electric field strength or electric field intensity at any point as F upon Q0, where F is the force experienced by a positive charge Q0 placed at the point. The test charge Q0 has to be very small so that it may not distort the field, which it has to measure. Since electric field intensity is force per unit charge, which is measured in unit per coulomb in SI units, it is a vector quantity and its direction is same as that of the force. The force experienced by a test charge Q0 placed in the field of a charge Q in the vacuum is given by equation 12.3 and equation 12.7 can be used to evaluate electric field intensity due to a point charge Q at the point distant r from it. Place a positive test charge Q0 at this point and the Coulomb's force at this charge will experience due to Q is F is equals to 1 upon 4 pi epsilon naught Q0 upon r square r, where r is the unit vector from the point charge Q to the test point where Q0 has been placed. The point where the electric field intensity is to be evaluated by equation 12.7. E is equals to F upon Q0 1 pi upon 4 epsilon naught Q0 r square into 1 upon Q0, where is equals to 1 upon 4 pi epsilon naught Q upon r square, and r is the unit vector.